we have assumed that when the charge carrier diffuses through the depletion region, then no recombination takes place. However, in practical diodes, it is not true. There can be certain ways by which electrons and holes can be removed from the depletion layer. Like, these electrons can come back to the donor energy state such that the ionized dopant atoms will become unionized, but the number of effective free electrons will decrease. And the second case is these electrons will interact with holes such that an electron-hole pair recombines, which ultimately decreases the concentration of both holes and electrons. The first possibility is not possible because we have taken depletion approximation to be valid, which means that all the dopant atoms, whether they are acceptor or donor, all are ionized. And the second possibility is not possible because of Shockley ideal diode approximation. The conclusion of considering these two approximations is that the probability of recombination is 0. But in practical diodes, it is obviously not true. Like, we will first consider the case of reverse biasing. In the concentration profile, the red line is representing magnetic carrier concentration in the p-type, which are electrons for the case of forward biasing, and the dashed line is representing the reverse bias case. Therefore, you can see in the reverse bias condition, the delta n is actually negative. The same goes for delta p. Similarly, in forward bias case, delta n is positive as well as delta p. Now, for the reverse bias casing, you know that the recombination rate is actually equal to delta n upon carrier lifetime. So, for the reverse biasing, it is going to be negative. One thing I want to make it clear that this lecture is very important for theoretical knowledge, not for numerical purpose. I will be telling you few formulas, but there is no need to remember them. Second thing is, the recombination rate which you are seeing here is inaccurate. The actual formula for recombination rate is very complicated, which is based on Shockley-Red-Hall recombination theory. But that is quite complicated for graduate level students. But if you are interested, you can have a look on this topic. This topic will include a lot of approximations, a set of new parameters which will make it little bit difficult for graduate level students to understand. The important point is that the recombination rate for reverse bias is negative. Negative recombination means positive generation rate. Therefore, in the depletion region, we have a generation current with generation current density to be equal to charge multiplied by intrinsic carrier concentration multiplied by depletion width divided by 2 into tau naught. Here, tau naught is actually equal to average of carrier lifetime of free electron and hole. The net reverse current density will be equal to ideal reverse saturation current density plus generation current density. The ideal reverse saturation current density, which is J0, is independent of the reverse bias voltage. However, generation current density is a function of depletion width, which in turn is a function of reverse bias voltage. Therefore, the actual reverse bias current density is no longer independent of reverse bias voltage. This is quite contradictory to the fact that ideal reverse saturation current is independent of reverse bias voltage. It is true that ideal reverse saturation current is independent, but the actual reverse current density that flows through the PN junction is actually dependent upon reverse bias voltage. Now, we will see the case of forward biasing. The recombination rate is positive. In the case of forward biased, recombination current density in the depletion region is equal to charge multiplied by depletion width multiplied by intrinsic carrier concentration divided by 2 tau naught into exponential of magnitude of charge multiplied by forward bias voltage divided by 2 kT. The net current density through the junction is equal to recombination current density plus the diffusion current density. And we know that diffusion current density can be written as ideal reverse saturation current density multiplied by exponential Q into forward bias voltage divided by kT minus 1. In terms of quasi-Fermi energy levels, which we just studied in the last lecture, we can also write quasi-Fermi energy level for free electrons in the depletion width minus quasi-Fermi energy level for holes in the depletion width is equal to charge on an electron multiplied by forward bias voltage. Upon conducting various experiments, it was noticed that at low current density, the recombination current dominates, and at higher current density, the ideal diffusion current dominates. To make things less complicated, this expression can be generalized as Here, N is called the ideality factor. For a large forward bias voltage, ideality factor is approximately equal to 1, as in such case, diffusion current dominates. And for low forward bias voltage, ideality factor is approximately equal to 2, as recombination current dominates in such cases. So, the value of N varies from 1 to 2 and it depends on the voltage applied as well as the semiconductor material. Since there is no clear boundary above which current level or the voltage level is high enough to use 1 as ideality factor, the ideality factor is generally provided in the question. You may study the same phenomena in BJT as well, and actually the use of ideality factor is more common there. In diodes, generally the value of ideality factor is taken 1 unless and until it is provided in the question. While reading books, you may get two statements which are quite contradictory. Like in some books, you may read that I0 increases by a factor of 4 for 10-degree rise in temperature, and you may also see in some books that I0 increases by a factor of 2 for 10-degree rise in temperature. You are never going to see these two statements in the same book. Actually, different authors may represent different parameters by the same symbol. This, when we talk about I0, which increases by a factor of 4, then the I0 is actually ideal reverse saturation current, in which we ignore the recombination current. Therefore, the reverse saturation current increases quite faster with temperature. But here we consider a practical diode, and in such cases, I0 is referred as reverse current which passes through the junction. Since for a practical diode, we are considering the recombination current also, the rate of increase in the absolute current decreases with temperature. Therefore, for a practical diode, we consider this case as it already includes the recombination current density. So, for numericals, you have to use the second formula. This lecture is not much important for numerical point of view, but still it is very important for theoretical knowledge. You have to remember only these two formulas in this lecture. First is forward current density and the second is the relation of increase in reverse saturation current with temperature.